Alrighty then. So what I thought I would do before I proceed is go through what I did in the first half and just kind of review a little bit about what we did, and maybe it would be good if we went through this and just kind of documented everything, perhaps with nice variables. So let's call this the sine wave. I think that's a good time. And then let's call this sine wave imaginary. You know, if you're going to do these sorts of things and get them to work, it's good to go back and do the documentation, because otherwise people don't know what you did and people can't remember. So now I've got here the original sine wave, and I'm going to do this for a copy. So why don't we call it sine wave FFT. And now I've got the sine wave, I don't know what to call this, sine wave FFT, sine wave imaginary. I compute the forward FFT. I get the PSD normalized. And so this PSD, I'm going to give this a name. How about we call it sine PSD. No noise. Okay. Now I go through and I get my sine wave, my original sine wave, and I pollute it with noise. I wonder if I should have made a copy on that. That's alright. So now this is a copy of sine wave with noise. Sine with noise. And now this is sine noise imaginary. Right, so that's clear. And now we have the forward FFT on the sine noise and the sine noise imaginary. We get the PSD normalized, and now we've got PSD with noise. Now what's this sine wave a sine wave of? That's the sine wave with noise, right? So that's a noisy sine wave. Let's write a comment in here. Display noisy sine wave. I don't know if it seems a little anal to you that I'm typing everything out and making it clear like this, but I gotta say, if I don't document it now after I just wrote it, I won't remember what I did. And this is the time to do it. So now I've displayed my noisy sine wave. That's fine. And now we're going to play the noisy sine wave. So why don't we say display and play noisy sine wave. So that's fine. Now let's go back to PSD. So now we got to display the PSD. Display. Now what is this sine PSD? That is the noise-free PSD for sine. And now we'll have a display of the noisy sine PSD. Okay. Now I got this thing here about the average. And this thing with the average, that really bugs me. Why is it that when we printed the average, was it so much further away from point 2 than
Yeah.
Well,
We have numbers between 0 and 0.5.
yeah, I mean, look at this. This is a very small number, 0.000 5, isn't it? 0.5, it would be minus 3. 0.05 would be minus 2. 0.005 would be minus 1. 0.0005? That doesn't seem right to me. This average noise power doesn't seem very good at all. But you know, if you think about absolute numbers, if you look at the noise that's coming in, look at it like this. This is 0.5 times what? 0.1. So that should be 0.05. And even if you square it, I don't know where these numbers are coming from, but I could tell by looking the noise power was right up in here. So for whatever reason, maybe I wasn't getting a good feeling for what this noise, what that should be in terms of noise. You know what I mean? Now someone said something about get the median. Would that make sense? Median's the middle. I could do that. Shall we get the median? mat1 dot get median. It seems like the median, it wants an integer array. So if I want get median to work with PSD noise, no, a cast won't work. I'll have to write my own median routine. Copy, paste. I'll have to do it with doubles. But your problem is your sort routine. Your sort routine takes doubles and returns doubles, so that's alright. Your middle has to go with doubles. Median is the middle, right? So I need doubles on here, which means it's got to return a double. Which means this has to return a double. Okay. So now I got a median. Double median equals, and now if you want I can print the median. Copy, paste, paste, median power. Let's see what that looks like. Median power is very similar to average power. It's a small number. You think 0.1 would work just as well? Let's try it. Maybe the squelch is too high. Actually, you know what? It did work pretty good. So let's put median power in here. Oh, I got a feeling you got to square the median power, or double it or something. 2 times the median. Wow.
Maybe we multiply the mean by 2 then.
Well, what if I took the median and I squared it? Small numbers that are squared make them smaller.
Yeah.
So what if I just say 4 times the median and just leave it at that? Wow. Now 4 times the median is I don't know, I think twice, it's about half the average noise power. So you're suggesting I could have done that with the average. average noise power, or the average, yeah, just take the average. So what if you threw the average in here? You might be right about that. There you go. See, we didn't need to go through that whole thing with the median.
Sorry.
No, don't be sorry. I was all over that. I was like, yeah, let's try the median. That's not your fault. I'm a grown-up. I took your advice. My fingers. So what I'll do here is I'll do it in terms of the average. Anything less than 4 times the average gets squelched out, and that should give us a relatively lower noise item. That's very good. I'm glad we went through this again. A very effective algorithm. Now, what happened here? We did this with a sine wave, right? Sine waves are probably going to be the simplest possible example and not a good test of robustness. So let's extract that method. You know what I'm thinking? Is let's set ourselves up with something other than here. We'll run the whole thing twice. Let's extract it into a method and call it noise reduced oscillator, sine wave. Sine wave. Okay, that's a good name for it. Now let's use our same noise reduction algorithm, only with a difference. And the difference is it opens up real audio data and then adds noise to it, does its little noise reduction thing with 4 times the average, and shows us the answer and plays the answer. Does that sound like a plan, sort of? So how shall we go about doing that? I'm asking you guys because you're the signal processing guys. You tell me.
Let's open the file.
Open a file. Yeah, good. How shall we do that? I mean, here it says oscillator. I don't think I need that. So see you later, oscillator. What we'll do is we'll go to the U-Law codec and ULC. Oh, I know. UL input. UL input. U input. Input audio. Input audio equals new U-Law codec. So that should prompt me for an input file. And then what we'll do is instead of get sine wave, we'll go to this input audio and we'll get the linear double data array. And all the rest of it looks the same. Now, here's a problem. How do I know this is going to be an integral power of 2? Ooh, ah,
You can use that mat1 thing.
mat1 dot make how does it work? Truncate to integral power of 2. Whoa, what an insidiously well-named method. That's a good one. I could tell you guys have been paying attention because I forgot. I always forget those things. Would that be better named something else? Not at this point. Wait till next semester. Yeah, truncate to integral power of 2. Yes, that's just what we want to do. So now the rest of it should be fine. Let's see what happens now. Oh, we need to pick a file. Well, that's a MIDI file, isn't it? I don't think we can do an FFT on a MIDI file. I think that would be a first-class horror show disaster. You have to convert it, right? You have to, you know, make a bitmap file out of it. So let's I think we need more delay. The delay has to be a function of the number of seconds on the input audio. Now, here's what I think. I think we can compute that. Integer, let's call this integer. That's not a good number. How about this? Double audio duration equals sine wave. Now I know I'm doing 8,000 samples per second, dot length, divided by 8,000. So that should give me the audio duration. So let's take that number and find out where we're doing the delay. That's here, right? So I want to sleep by audio duration times 1,000 converted to long, because he wants it in milliseconds. What do you think of that? So if audio duration is 3 seconds, I want like a number like 3,000 to come in here. So how's that grab you? Good, right? Oh, right. This is another reason you don't want to start with real audio files, because you don't want to have something which requires you to interact with a standard file open dialog box during the debugging phase, because it'll slow you down and drive you nuts and make your wrists hurt. You know, I think we need to add an extra second just because it's playing right after the other thing. So let's say 1,000 plus. So we'll have however long it takes, then we'll wait a second, and then we'll start. Here. So it got rid of a lot of noise, but it also sounded like it got rid of a little high end.
It's too high in there.
Yeah, I think what's happening is our squelch is reducing our some of the important information. So I'll just modify my average a little bit and see what happens. Oh, I didn't actually look at the average outputs, did I? That might be good to know. Well, I can see that a lot of noise has been reduced, but I can also see some harmonics are gone too. Oh, I didn't actually print out the averages at all, did I? Alright, well, I gotta say, we had some pretty good results here. This is the data after. You see what's happening here? There are definitely places where we've taken the signal and just chunked it out. Right? There's whole areas in here where it looks like there's no signal at all. And this is our whole sort of spectra that sounds like it's missing. And if we look at the signal sort of with noise, there's a whole big pile of noise in here. So maybe it's time to sort of muck about a little bit more with the fudge factor that we have in here. Was it 3? How about if we just said 2 times the average? Right, this is why it's so important to try it with real audio as opposed to just a sine tone. I'm going back down to the average here. So let's just give it the average and see what happens. Interesting, isn't it? So there's a little noise, but it's not too bad. I'm liking the use of the average in this particular case. On a real audio signal, average just seemed to pay off. Now let's try a different one. Let's try space music. Same settings. Fun, right? Isn't this fun? Very fun. It wasn't too much better. So now I'm going to crank my fudge factor up. Squelch control like that might be something you have to adjust. If you had a ham radio, you would have a diddle on the squelch control, and you would have to decide what's noise and what's not. That's much better. That was a lot better. And there was some good high end there too. So I think that we have a reasonably good, robust algorithm, but it requires a little bit of adjustment on the squelch control. You know, that this part in here, look at that. There's definitely gullies with which it considered to be noise, and it just zeroed it out. So we're almost out of time, and I'm thinking that the next homework assignment is just like this one, only with a difference. And the difference is it's autocorrelation time. So what do you think of that? Time for an autocorrelation. Let's do something with autocorrelation. Assignment. And we'll give this assignment a name. Let's call it Homework 7. Is that a good name for it? Because Homework 6 was the equalizer. And we'll call it, what shall we call it? Autocorrelation with FFTs. How fun is that? So, for next week, write a program that uses fast autocorrelation with FFTs to reduce noise in a now for the input signal, I don't think we should use a a regular input file. I think we should use a simple 440 Hertz tone. So let's use, yes sir. Well, we use the oscillator that I did in class. So noise in a 440 Hertz tone that is 2 to the 13 samples in length, and I'm going to guess that's 8,192. And then I'm going to say that I want to hear it, and I've been having a little trouble compiling your code. So how would we find a way to input the AU file or export the AU file so that I could hear it? Save the output file as an AU file so that we can hear your results in class? Yes, sir.
Do you think there must be a way on Blackboard to allow multiple submissions so we can submit our code and our AU file?
Yes, or what you can do is you could submit it as a Word document that I can click on with the AU file built in with audio. You know, can't you paste It won't let you put in a Word
Oh, no,
document?
you can, but remember last time I had to email it to you?
You said you couldn't play my AU file from my Word document, so.
Oh.
What I did the last time was I played it and recorded onto my Windows recorder at the same time, and then I just gave you that.
You shouldn't have to record it with Windows Recorder.
You just upload it there.
Isn't it, I got confused.
Oh.
Isn't there a save on this? Here, ulc1.save, save AU file. That saves it, right?
Rich brought up good point, which is zip.
Yeah, but I mean, Mike says he has to record it with Windows Recorder. And I said, no, you just save it by calling the save file function and it will save it. It'll even prompt you. So in theory, if I run this, it should prompt me for a cleaned up file, I think. Yeah, and then it says select an AU file for save. So that's, he wants a file name. Well, I'll leave it to you. How else should we do it? You want to use a zip file? That's all right with me. I just want to somehow realize your work in the classroom so that we can all see it together. And if you used a Word document, you could take a screenshot, and that might be good. Save the file as an AU file so that we can hear it and save the screenshots in a Word document. Is that fair? So I mean, if you want to use a zip file, you can. And if you want to do the multiple upload thing, it should be possible to do that here within allow unlimited attempts. How's that? And then due date. And then enter due date 18th, enter time 2 p.m. and then all students individually, and that's it. Does it make sense? Are we there? Submit. And now I think maybe we're ready to stop this.